Hello again. So now we're going to look at the reciprocals of cosine and sine. So remember, 1 over cosine is secant. So this is the graph of secant. Now notice they've sketched in the graph of cosine. So whenever you have to graph secant or cosecant, what you do is you graph sine or cosine, and then you just go figure out where are the asymptotes, where are the high and the low points, and then just go hug the asymptotes from there. So, like, those are the points that you really want to focus on in this mess is here, here, here. It's like, where are the asymptotes? Where are the max and min points? And the asymptotes are just the 0 points on cosine because 1 over 0 is infinity, so. But just like I said before, these have asymptotes, and one of the questions will be, where are the asymptotes? So for the original graph, they occur at pi over 2, and then at 3 pi over 2, 5 pi over 2. So this is pi over 2, and then the width here is pi, because a full period repeats on 2 pi, and the asymptotes are occurring at every 0 point. So oh, well, they just got lazy. X cannot equal pi over 2, absolute value of b, k, where k is not integer. Yeah, technically that works. But it only works if it's centered. If the graph gets shifted, this is not going to work. Now our range, I do want you to note this, the orange graph is not part of the graph, it's just there to show us where to find the highs and lows and the asymptotes. So the graph itself actually has a giant gap in the middle. So there are no values in the normal cosecant. The function does not have any y values between -1 and 1. It will hit -1, it will hit +1, but it won't hit anything in between. It will never cross the x-axis. So it has no x-intercepts, and instead it just gets funky asymptotes. There is no amplitude. There is technically, but since we don't bother graphing the points to the side of those highs and lows, like paying attention to exactly where they go, there's no visible effect. But technically, it will like get steeper faster if the number's big. If its number is negative, it will still cause a vertical flip. So like these numbers all do the same thing. It just looks a little different. It's also the amplitude will impact, like the amplitude on the cosine graph like moves those highs and lows further apart. So that does happen on the secant graph. So saying there's no amplitude is like, all right, so let's see this crazy mess. So remember I said, first thing we're gonna do is we're gonna figure out what's going on with the graph of cosine, but everything else is the same. Ugh. Honest, I can write. All right, so our amplitude is 2.5. And then our period is 2 pi divided by 0.4. 0.4 is 2/5, or just 2 divided by 0.4, crunch, crunch, is 5. So this is 5 pi. So our period is very weird. Very, very weird. All right. So let's see if we can't graph the cosine from that. And then we'll go back and sketch the secant in from that. Okay, so we're not shifting left or right, we're not shifting up or down. So our cosine graph, remember just the basic cosine shape is like this. So normally it would start at 1, but we have an a value. So the cosine graph would start way up at 2.5. Then it will go to 0. Then it will go to negative 2.5. Then it will come back up. And then it will go up again at 5 pi. So there's the width of our period. So playing the let's cut this in half game, 5 divided by 2 is 2.5, or 5 halves pi, 5 pi over 2. Half again is 5 pi over 4. And then halfway between 5 and 5 halves, or 5 and 2.5, that'd be like 3 and 4.5, 3.5 and 4, so it's 3.75 pi. Which is 3 3/4. 4 times 3 is 12, plus 3 is 15, so it's 15 pi over 4. But that is also something you could crunch on the calculator and get the fraction that way. So I'm just finding the average between 5 pi over 2 and 5 pi, or the average between 5 halves and 5. Add them together, divide by 2, fraction, just stick the pi back on. All right, so we have where the marks go, our highs and our lows. So all right, there's one period of cosine. Now, everywhere there is a 0, secant will have an asymptote. All right, and then our high and our low points still stay the same, but this one, since it's above, we're gonna like mirror image the shape of the graph down here. It'll shoot down up here. It would go up, which also means it would continue on. There would be another asymptote. So again, the asymptotes are vertical lines. It starts at 5 pi over 4. And then, so the distance between asymptotes, like there's one at this 0, and then the next 0. Well, the next 0 is the period apart. So this one in between is half the length of the period. So I take my 5 pi over 2, and that gets a k, where k is any integer. Yeah, I know up earlier it said k is any odd integer. You should not confuse the notation like that. We should consistent, just keep k, same thing all the time. Really what it means is whenever you use k, you need to define what you mean with it. Did you mean any integer? Did you just mean positive ones? Did you just mean the odd ones, the even ones? What did you mean? But we graphed one period of secant by graphing one period of cosine. Now down here, well, let's do it with all the ugly mess. All right. So again, we're going to graph it like it's cosine. So our A value is 4. So the cosine will have an amplitude of 4, which means up 4 versus down 4. So the highs and the lows of secant are going to be 8 units apart. All right, we need to see the factored form. So this would be pi over 3 times x minus. And so we're asking ourselves, pi over 3 times what gets us back to pi over 2? So let me just kind of thought bubble this. In order to figure out what that is, we are going to divide by pi over 3, which means we really multiply by 3 over pi. Because if I do that on both sides, then I can clearly see the 3's cancel, the pi's cancel. So my unknown thingy is 3/2. So that is what would go inside the parentheses here. So our period is 2 pi divided by pi over 3, which means times 3 over pi, pi's cancel, and we get a period of 6. All right. Now our h here, the x minus 3/2, tells us we think minus would go left, so it's really going to go right. Right. 1.5 units. And then our k value, the whole graph is going to get shifted up 1. Okay. So now we're going to try to graph this insane mess. So it's going to go right and up. So let me just move that a tiny bit down. So our normal cosine graph actually starts above the x-axis, but if we think about that 0, 0 point and we shift that around, then we can find the cosine point off of that new location. So our whole period is 6, but we're moving 1.5 units right. So let me just mark 1.5. And then if I add 6 to that, I get 7.5. Halfway between is 4.5. Halfway between 1.5 and 4 is 3. And then over here, it'll be 6. And that's just me being comfortable with my numbers. But this was our starting number. 7.5 is our starting phase shift number plus the period length, then the average between them, and then the average and the average again. So there's all 5 of those x value or input numbers. Now, worst case scenario on these, like you can take 1.5, plug it in there, see what happens, and then plot that point. All right, so we had our 0, 0 point is to the right, and then it's also supposed to be up at 1. So I'm gonna, and this is that midline they talked about. All right, now our amplitude we actually need to take into account here. So this is 1, but our amplitude is actually 4. So I want to go 4 units above and 4 units below this not line. So 1 plus 4 goes up to 5. 1 minus 4 goes down to -3. So there's my highs and my lows. I got my starting tick number, all my other ones. So the actual graph will start 1.5 units to the right and up 1 plus the amplitude. Then at our next tick mark will be at 0. Our next tick mark, sorry, our 0 line, which is 1. Our next tick mark will be down here at -3. The next one will go up to the new 0 line, which is at 1. And then 7.5 will go back up to 5. So there's those 5 key points for the cosine graph. Now, wherever the 0 points were on the midline, that's where our asymptotes go. So it's not where would the cosine graph equals 0, because the period and the phase shift number in there are going to mess with that. If you're not sure, if we plug in 3 times pi over 3 is pi minus pi over 2 is pi over 2. Cosine of pi over 2 on our normal graph is the second point, which is 0. So this is where the asymptotes occur. All right, so if it was 3 and 6, that also means 0, but usually when they write these equations of the asymptotes, they want you to just whatever the first number you got from the graph was. So x equals 3, and then to get to the 6, it's 3 times k, or this could also be x equals 0 plus 3k, which would just be 3k. Again, with our normal, k is an integer. Which a really lazy way to write that is k with this little e, and then I'm tired of writing the word integer symbol is this kind of bolded z. I'm only pointing it out in case you see the notation in some of the YouTube videos. That's just another way to say the same thing. All right, so now we actually got to graph the mess. So we take our high and our low points, those stay, and then we're going to go hug the asymptote. Hug down, hug back to the right. There it is. That is our graph of one period of this crazy secant function. If you can graph the cosine, you can graph the secant. You just got to get used to that thoughts of where are the asymptotes, where are the highs and the lows. And guess what? Down here with cosecant, it's the same thing. Start with your graph of sine, where are the asymptotes, where are the highs and the lows, and then just go hug your asymptotes for the graph. Now, because sine is 0 at 0, we start with an asymptote on that axis. So unless the graph has a horizontal shift, it's going to stay, and that's actually going to make our asymptote formula look a little weirder. Okay. All right, so down here, they give us this crazy mess. So again, we're going to graph the sine, sketch it out, and then they asked an extra question here, domain and range of this function. So this is a very sneaky way of asking, where are the asymptotes and where are the high and the low values? All right, so our A number is 2. Our period is 2 pi over pi over 2. So this equals 4. All right, so our period is going to go 4 units wide. Well, that's going to be really nice for our subdivisions. And then we have so this goes up 1. All right, so let's go ahead and graph our sine. So we don't have a left or a right shift. Yes, score. But we do have that up 1. And that's just where we're going to count our amplitude on the sine graph from. But because we don't have a left or a right graph, our sine graph will start there at 0, 1. Now remember, our normal sine shape is start at the 0, up 0, down 0. All right, so the up, the 0, the down, the 0. So this other 0 occurs here at 4. So we need to know, what are these tick marks? Well, halfway between 0 and 4 is 2. Halfway between 0 and 2 is 1. Halfway between 2 and 4 is 3. Now, the how high do we go? That's where our A value comes in. So from our new midline, it's going to go up to 3 and down 1, down to -1. All right, so our graph goes up first, back to the 0, and then down and back to the 0. So that is the graph of sine. So now we are going to graph cosecant. So everywhere, every one of our 0 points, that is now an asymptote. All right, so asymptote, these are x equals. So at this one we got 2, 4, 0. So I'm going to start with my starting number because in the examples there might be a phase shift, a horizontal shift. That's what goes first, plus our distance between asymptotes is 2 times k, where k is any integer. So if those are where the asymptotes occur, then that means the domain is everything except and we don't typically write these kind of repeated domain restrictions in interval notation. It's a giant headache. I mean, I suppose we could, but it's a headache. All right. Now our secant graph, zoom back in here. We'll go through this point at 3, and then it'll go hug the asymptotes. It'll go down here at the x equals 3, y equals -1, and go down and hug the asymptotes. So our range on the upper half of the graph, the lowest we get is 3. On the bottom half of the graph, the highest we get is -1. So our range is going to go to, so from -infinity to our lower point was -1 with a bracket. And then our upper bound there was 3, which also gets a bracket. So the sine's range would be from -1 to 3. So the inverse of sine's range is the other side. That just kind of like nicely works out that way. But these reciprocals are not inverses. Inverses, I have to be able to put one inside the other and get my undoing and canceling. These don't undo each other. They cancel if we multiply them. So I just want to like try to get that idea started that we haven't looked at the inverses of any of these functions yet. All right, cut this one here.